judge, and you judge delay by taking d over tau, per tau double. The Bode stability criterion, absolutely no problem with the time delay. Here's what it boils down to, and we're going to do that, of course, on Wednesday. We do a Bode plot of the product of all the transfer functions in the loop. Remember, the denominator of the closed loop transfer function is 1 plus product of everything in the loop. So we have to do a Bode plot of the product of everything in the loop. And then we look at what is the amplitude ratio at a particular frequency. And the frequency will be the frequency when the phase lag is minus 180 degrees. So we are going to be looking for the Bode stability criterion. We have two plots. We have the log AR plot, and we have the phase lag plot. All we will have to do is look at minus 180 degrees. Find the phase lag that we have at minus 180. Go up or down until you meet the log AR plot. In this case, I would go down. And go to the left. If this number is less than 0, we are closed loop stable. If this number is greater than 0, we are closed loop unstable. It's that easy. We just do it, and you can see why it's easy to do it in one plot instead of having to work with plots up and down. So that's what it boils down to. And if you look at the software,
if it's negative, it's stable.
If it's negative, it's stable. If you look at the software, then you can just put that Bode plot here. You will see here a couple of points. I'm finishing with it. You'll see here a couple of points that have special values. Minus 180, you see right there? And the 0 here. Okay? So, you draw the line from minus 180 until you hit the brown curve. Up or down until you hit the orange curve. Left. If you go below the 0, you're stable. If you go above the 0, you're unstable.
So you're not stable.
In this case, let's see, minus 180 brown. Yeah, I would be unstable. If that was an appropriate plot. Okay? This is not an appropriate plot. This is not a Bode plot of everything in the loop. Okay. You have to do a Bode plot of everything in the loop. All right, guys. That's what is on the menu for Wednesday. Felix, your question.
Can you say that one more time?
We're talking about that all day Wednesday. I just want to give you a preview.
A sneak peek.
A sneak preview about, you asked me what you asked me what's good. No, Mohammed asked me what's good for. So one thing it's immediately good for is for closed loop stability. Okay? For closed loop stability, we can immediately use Bode plots. We have to do a Bode plot, not of GU, but of GOL, but of the product of everything in the loop. So GU-GC, with class notation. So I would have to have a GC, do a Bode plot of GU times GC, and then you immediately know if you're close to stable or not. Okay? All right, guys.
We're good to go?
I can't believe
We're done for today?
Oh, wait a minute. Oh!
No!
Half an hour. No, we're not.
Hell, man!
Oh, boy. Sorry, guys. Okay, half an hour. Good. Okay, what is the good criteria? Good. Oops.
I can't believe
My mind was 15 past, but that's the break for the... All right, what is the good criteria?
Fuck, I shouldn't have said anything.
No, you should have. You should.
Oh, boy.
You should have just stood up and left.
I should have just, yeah.
Like, all right, bye.
Didn't get much sleep last night, so...
I can't believe what you just did.
All right.
Dude, I
too,
We move to the next topic. What is the stability criteria?
It's all your fault.
Damn.
We're going to do that so much on
Now,
Wednesday.
as I'm behind on time, I am not going, I have in the notes kind of a justification, a semi-proof of the Bode stability criteria. I don't have, well, we'll see. If I have some time, I'll do it at the end. Let's talk and understand the Bode stability criteria.
Just explain it really
Damn it.
And that's for closed loop system. First important thing applies only to open loop stable systems. So if the system is open loop unstable, and I'm asking you to do a body stability, the question that got that student really mad, I gave them an open loop, unstable transfer function that was third order denominator. I gave them GU with a third order denominator, and the question was, what do you conclude from the body stability criteria? I didn't say anything about using the Ruth array. I had said in class how you would do something like that.
But he just had.
So, even though the problem didn't say anything with array, the very first thing you check is, are you open loop stable? So how would you check the stability of the open loop transfer function with the third order denominator? But the Ruth array. Okay? You're not allowed to calculate the roots. Ruth array. And if the Ruth array gave you that there's a sign change in the first column, the answer is body stability criterion doesn't apply. I can conclude nothing about closed loop stability. And that's the full credit correct answer. So there's a problem that I was checking. If you did the Ruth array correctly, and you said body stability criterion doesn't apply, full credit. If you did the body stability criterion without checking stability and conclude something, you got no credit. Okay? So, very important, applies only to open loop stable systems. There's a second conditional application. Clear answer if there is only one frequency at which Gaussian plot of GOL. I'm using the symbol GOL. Yes, Andrea.
I'm very confused about that saying for closed loop and then why something open loop.
Because it requires open loop stability to be able to judge about closed loop stability. Okay? If it's open loop unstable, you cannot use it. Then you have to use the Nyquist stability criterion, which is the last stability criterion we're going to talk about. Okay? But if it's open loop stable, basically it applies. There's a second condition at which body plot of GOL equals product of all three F's in the loop. There's only one frequency at which body plot of GOL has phi equals minus 180 degrees. So if your phase-like plot looks like that, minus 180, only one intersection, this is the phi plot, you're fine. If it looks like that, you're fine. Only one intersection of minus 180. But if it looks like that, and here is minus 180, so here you have three intersections of minus 180, it's not clear. Basically, if all of them satisfy the condition, you're okay, but if some do and some don't, you can make a conclusion. But this is a rare situation, okay? So, but here's what it is. So this is the main thing. That's the one I'll underline. Do body plot of GOL, which is GU, GC for class notation, equals product.
Can you go over those two graphs again?
Say again?
Could you go over those two graphs again?
Well, let me write it and then I'll go over it.
Okay.
So, do body plot of GOL, which is the product of GU-GC. I call this the total open loop transfer function. It's the transfer function that you have when you do the loop. And let's say you have boxes. If you were to open the loop here, if you were to open it here, the transfer function between this signal and this signal is the product of everything in the loop. That's G, when you open the loop like that. I don't know, GOL is the best notation, but that's what I call GOL, the product of all TFs in the loop. So, example, if I have this GU of S, which you know is open loop stable, and here is the GC, and let's say I have a PI controller 3, 1 plus 1 over 6. So this is a PI controller. This is my loop. What is GOL of S? The product of everything in the loop. What do I have in the loop? This times this. So in this example, GOL is okay, that would be GOL.
Ah.
The product of the two transfer functions. So, do body plot of this GOL. Okay? The closed loop system. Now, that includes GC. We're talking about closed loop stability. So GC is a big part of it. Okay? The closed loop system is stable if magnitude of GOL at I omega C naught is less than 1, where the crossover frequency, that's a new term, course, magnitude less than 1 is the same as log of magnitude negative. Okay? This is the same as log of magnitude of GOL. So, the two conditions, open loop stable, that's the first condition we must have, and the second condition, 1 omega sigma. So there's a unique frequency at which the phase lag becomes -1.
What does that CO stand for in the
Crossover.
cross?
Yeah, it's called the crossover frequency. Don't ask me why, I don't know. Mika.
What's in the small box ready for the transfer constant?
A PI controller with KC3 and tau I 6. It's a transfer function of PI controller with KC3. Is that the correct sign for KC? Since it's open loop stable, the sign of KC should be the same as the sign of G of 0.
Should be positive, right?
So what's the sign of G of 0?
Should be positive.
It's positive, right? If you put S equals 0 on this, what do you get? +1.
Plus something.
So G of 0 is positive. And we check this quadratic has all positive negative real part. So for an open loop stable system, KC should always have the same sign as G of 0. So it should be positive, so I picked the correct sign for KC. We know it's open loop stable. It's a closed loop stable without control loops. Okay? So let's use the Kotte stability criterion to check if we are closed loop stable. So the first thing I need to do is rewrite this in the form that the software uses. So I'll multiply through to write the ratio of polynomials times into the delay. So the denominator polynomial is 6s times this. So I'm writing it with both power first, so 6s plus 18 s squared plus 60 s cubed. And numerator is this product times 3. So I have 1 times 3, 3. And then I have 6 plus 5, 11 times 3, 33. And then the quadratic is 30 times 3, 90. So that's the GOL for this example. Okay, everyone? Okay. I just GU with a delay times GC, and I rewrote that, making common denominator. Okay, I rewrote this one. So multiply through. Okay. So let's go back to the software. And now we'll be able to check the bus again. Okay, so delay 7. What's the degree of the denominator?